Valence form such a two-particle system in which they will couple with each other and they are not separable, we will write them as sine, and this is R1, R2 equal to some constant. Here this constant is 1 over square root 2. And then, as we are not able to say which particle is in which state, so I will write psi A and R1, then psi B R2, plus psi B R1, psi A R2. Got it? Why I am doing this? This is a wave function. This is a state. Now this state is having the coordinate R1. This is having R2. Now as I cannot say that which particle is in which state, so I am writing plus psi B. Now I am giving to psi B the R1. Into psi A the R2. Now you have added two different combinations. When the states will be orthonormal. Orthonormal means when they are orthogonal as they are having the magnitude 1 orthonormal, normalized. What will happen if you add them up like this? 1 will come from here, 1 will come from here, 1 plus 1. And then take a square root of it and you will have square root 2 here. So that's why this state is in orthonormal state. This and this combination are actually the same. Look here. Here it is up and this one is down. Consider this up and this down. And now for the next one, this one is coming down while this is coming up. So it will be either this combination that I will have plus here, or I can have minus here as well. This is also possible. Like in this state I am having minus. While I was having in the triplet combination, in one of the triplet combination, you know, one of the triplet combination was that both are up. One was that both are down. And the other combination was that one is up, the other is down. Plus, one is down, the other is up. It was with a plus here. So we were having the addition. And here I am having, in a singlet I am having minus. So I can put plus and minus with such a coupled state in which I cannot say which particle is in which state. I will write plus minus here as well. So I will represent psi plus with a plus sign here and psi minus with a minus sign here. And this will give me further information. For the means at hand, I will say that when I write psi plus, then it will be for the bosons, and when I write psi minus, it will be for the fermions. Now this is like a postulate. This is like an axiom. Means this is the truth. This I will have to accept. Clear? Later on, it will become clear to us that why this one was assigned to the plus, to the bosons, why the plus is assigned to the bosons and the minus is assigned to the fermions. At the moment, it's just a postulate. It's a truth that we will have to follow. It will satisfy. Clear? Now, you know about the bosons and fermions. Bosons which are having integral spin and fermions which are having half integral spin. Clear? So the difference between the two is in their spin states. Okay. Now you can see here that why I am assigning minus to the fermions. Why not plus? Let's say I am writing that the two fermions, let's say, occupy the same state. What will happen to this equation? Psi, this will be R1, R2, and this is equal to A times psi A R1, while psi B R2, it will also become psi A. The next state is also psi A and R2 minus psi B. So it is psi B and R1, psi B R2. Clear? So you have combined the two states here. Okay. What I will do here, that psi B, what I did, that psi A is equal to psi B, means both the particles are in the same state. This one, psi A, psi B. Now when both the particles are in the same state, so my expression will become that wherever I am having psi B, I will make it psi A. And what will happen to this one? Are they cancelling? So we will get 0 here. And what this means, that psi R1, R2, it's a coupled state. It's a combined state of the two. This is equal to 0. Such state doesn't exist. Means the fermions cannot be in the same state. Pauli Exclusion Principle. So this is the Pauli Exclusion Principle. Okay? The Pauli Exclusion Principle. No two electrons can have the same quantum state. That's why the minus I gave to the fermions. While two bosons can be in the same state. Like for two bosons, such a state exists, it will not be equal to 0. So the plus I give to the bosons, the minus I give to the fermions. Clear? We can call them coupled state, entangled states. You cannot separate them out. So I can say that as they are the same state, let's say I'm having an operator, and that operator is such that if I apply, let me call this an interchange operator. Okay, this is an interchange operator. So what this operator does? This operator actually exchange or interchange two particles. For example, I am having psi or f, it's the same thing. Let's say you are having a function, or let me write instead of f psi. Psi, it's a coupled state, and if I apply this p operator on it, what it does, it make it psi r2 r1. From r1 to, it changes the wave function to r2 r1. So it has exchanged the coordinates. It says exchange the states with each other. Clear? You are getting it. It's an exchange operator. It interchanges the coordinates with each other. And now if I apply it again, like on this one, I apply P sine R2, R1. What will happen to this one? It will become sine R1, R2. Means you apply it the next time, you will get that wave function back. So that's why I call it an exchange operator. Interchange operator or exchange operator. What does it mean? If I apply P square, it means that if I apply P and then dot P on sine R1, R2, I will have sine R1, R2. Clear? Means once you applied it, interchange the coordinates. You applied again and it gave those coordinates back. So it means in P dot P or P dot P I can call P squared. P squared applied sine 1 R1 R2. It will be again the same state. Clear? It will be again the same state. So P squared, it tells you that the eigenvalue means P square here is equal to 1 because it doesn't changes the state. Clear? P square is equal to 1 here. It's just like 1. When I applied P, it changed the coordinates. I applied it again, it gave me those coordinates back. It means that if I apply P twice, I will get the same state. So P twice means P square. When P square is applied, the state remains unchanged. So it means P square is equal to 1. So from here, the eigenvalues of this operator are plus minus 1. When P square is equal to 1, then P will be equal to plus minus 1. So this is an operator which I call exchange operator. It changes the coordinates, and the coordinates, if I apply it again, I will get those, it will again change those coordinates and I will get those coordinates back. Clear? So for this P, I can write that when particles will be identical, then I can say that this P is commuting with H. H is the Hamiltonian. It commutes with H. Clear? You got this point? Means when you operate P, the Hamiltonian means it will interchange the coordinates. It will just change, means it will move particle one particle to R1, the other particle to R2. When you apply the P operator, particle 1 is, okay, let's understand it here. If these are distinguishable particles, okay, this is your psi A state, this is your psi B state. This is R1, this is R2. Clear? If these are distinguishable particles and you interchange them, now you know that the particles are not exactly in the same states. But if they are identical particles, what will happen? Can you say that the particles are not in their states? No, we cannot say, because these are same particles. These are identical particles. You exchange them. So now what you have done, you cannot say that you have generated a new configuration. It seems the same. You again apply P on them, exchange operator, again it will be the same configuration. Clear? You are exchanging the particle between the states. Or you are saying that you are changing their states. If this is the situation, the energy of the particle, what will happen to the energy, to the Hamiltonian of the particle? It will also remain the same. Hamiltonian means the energy earlier and the energy after the exchange. It will remain the same for the identical particles. For the distinguishable particle, it will not remain the same. The red and the blue, it will have different configuration. So for identical particle, then I say that the exchange operator commutes with Hamiltonian. Now, what is meant by commutation? When two operators commute, what is meant by their commutation? Those two operators will have the same set of eigenstates. Their eigenvalues will be different. Means here the eigenvalue of E is 1. 1 plus 1 are minus 1. It is not necessary that Hamiltonian will also have the same eigenvalue. Its value will be different. But the eigenfunctions for both of these operators will be the same. They will share the same set of eigenfunctions. Clear? Whenever two operators commute, then those two operators will have the same set of eigenfunctions, while their eigenvalues will be different. Okay. So I can easily say that if this p square is plus minus means this p is plus minus 1, so I can write from this equation that sine r1 r2 is equal to plus minus sine r2 r1. This is clear?
Yes, sir.
When psi r1 r2 is equal to psi r2 r1, here r1 r2 and equal r1 r2, you got it big, you come here, p here, operator here is from this position. Let me explain this one. P operator is operating on a wave function, it will give eigenvalue here. And the eigenvalues are now 2 plus and minus 1 for the P operator. So this will be either plus 1 or it will be minus 1. So I have written those here, plus and minus 1. If you exchange the coordinates and plus comes in, so no problem. And this will be one kind of wave function. And if I exchange the coordinates and minus comes in, then it will be another kind of configuration of wave function. Function will have a different property, and we call them is if you change the coordinates, you call in the wave function or the function remains the same, you call it symmetric. And if you change the coordinates and the function changes its sign, then you call it antisymmetric. Clear? You know this thing? symmetric and anti-symmetric. Let me explain this further. But I will explain symmetric and anti-symmetric in a while. But first understand this one, that how we came to this one. It is clear to all of you, or I repeat it? Okay. I'm having a wave function, and this wave function is a coupled state. Coupled means two coordinates R1 and R2 are being coupled. If I apply an operator such that the operator changes the coordinates, P operated on this one and it gives me the function with exchange coordinates. For R1 I am now having R2 and for R2 I am having R1. It exchanged those. Then I said that if